Okay, thank you very much. Ευχαριστώ. Kalispera. That's the end of the Greek. Okay, so in this talk, I would like to share with you what we do at CERN, what we do in particle physics, and specifically what we're doing with the Large Hadron Collider at CERN. So many Greek physicists are involved in these activities, so this actually also belongs to you. So basically what we're trying to do is address some of the very basic questions about human beings, their place in the universe, that are summarized in this picture, I'm sure you know it, by Paul Gauguin. So these people are asking themselves some very basic questions. Where do we come from? What are we? Where are we going? And I would argue that these are precisely the questions that we physicists, we particle physicists, are trying to address. So on this slide here, I show you an outline of CERN on the outskirts of Geneva. This white line here is the Large Hadron Collider. Large because it's 27 kilometers in circumference. You can compare it to the size of Geneva Airport over here. And one way or another, CERN and the LHC have been in the news quite a lot in the last few years, in particular in connection with this particle known as the Higgs boson, which I will try to describe to you later on. So this is actually a picture of Peter Higgs. So he came up with his theory about the Higgs boson back in 1964. This picture was taken a little bit later in 1965, and here he is working out some details of his theory, which maybe you can steal from him if you can read what's written on his papers. So one of the things I want to discuss in my talk is the path leading to the discovery of the Higgs boson, but I also want to talk a little bit about what may lie above and beyond the Higgs boson, for example, the origin of dark matter, the origin of matter in the universe, and many other fundamental issues. So let me start off with this logarithmic scale, this slide rule, which shows you all the scales going from the size of the universe, the visible universe today, which is 10 to the plus 28 centimeters, all the way down to the smallest scales that we physicists speculate about at the beginning of the Big Bang, something like 10 to the minus 32 centimeters. So 10 to the 28 is a very big number. And the way that I like to describe it is think of the American budget deficit, express it in cents, and square it. And then you get a number something like 10 to the 28. 10 to the minus 32, that's very small. So somewhere halfway along this logarithmic scale, you have the human scale. So this is a picture of Albert Einstein with his kid sister when they were little children, about a meter tall, something like that. Now, of course, we know quite a lot about what goes on inside, or what went on inside Albert Einstein and his kid sister. We will know that they were made of molecules. Those molecules are made of atoms. Those atoms contain nuclei with electrons and clouds around them. Those nuclei, those are made of objects called protons and neutrons. And if I'd been giving this talk 80 years ago, I might have said, well, protons and neutrons, those are the fundamental constituents of nuclear matter. That's the answer to Paul Gauguin's question, what are we made of? But now we know better. We know that inside those protons and neutrons, there are things called quarks. And as far as we can tell at the present time, quarks, electrons, and related particles, those are the answers at the moment to Paul Gauguin's question. Now, if you look at the universe on the very large scale, you see structures. You see galaxies, you see stars, you see planets. And one of the things that we don't understand is how those structures came into existence. We know what those structures are made of. They're made of molecules and atoms, just like what we're made of. But what pulled them together, we don't know. We think there is something called dark matter, and I'll come back to dark matter in a moment. That dark matter, we think, is possibly made of particles that we may be able to discover in the future at the Large Hadron Collider. What we're doing directly with experiments at the Large Hadron Collider is we're looking deep inside the structure of matter, so you can regard it as being a sort of super microscope. But also, in some sense, we're looking back to what happened at the very beginning of the universe, back very soon after the Big Bang. And maybe, for example, we'll find there the origin of dark matter, the origin of the matter in the universe. So the Large Hadron Collider, it is a super microscope, but is also, in some sense, a super telescope. Now, a lot of what we know about particle physics, we first learnt by looking at energetic particles coming from outer space. As you probably know, the Earth is bathed in what are called cosmic rays, first discovered by Victor Hess in 1912. So he discovered these energetic particles coming from explosions out in space, whose origins we still don't fully understand. When these energetic particles hit the upper atmosphere, their energy is converted into large numbers of other particles of different types. And in the first half of the last century, many of the major discoveries in particle physics were made by looking at these cosmic rays. But if you want to study in detail what is happening in those collisions, if you want to understand in detail what we are made of, then you need to do experiments in the laboratory under controlled conditions, and that was how, around the middle of the last century, people start building large particle accelerators to study the laws of physics in detail in the laboratory. So what did those studies reveal? They revealed something that we call the standard model of particle physics. So this was proposed in the 1960s by Abdus Salam, whom you see here, originally from Pakistan, and two American theoretical physicists, Glashow and Weinberg. And their theory of the structure of matter, of what we're made of, makes essential use of the ideas proposed by Peter Higgs, whom you saw a few slides ago. So the first experimental confirmation of predictions of this theory came in the 1970s in experiments at CERN, more experiments at CERN and elsewhere in the 1980s, the 1990s, confirmed many of the details of this theory. So what does this theory, what does this standard model contain? Well, on the one hand, it contains the particles that make up matter. The answer, if you like, to Gauguin's question, what are we? So the particles of matter, here we see a list of them. On the left, we have the quarks. There are, we now know, 6 different types of quarks. For example, the strange quark, which was first discovered in the cosmic rays. Then over on the right-hand side, we have the electron. And we know now that there are 2 particles very much like the electron, but heavier. One of them is called the muon. That was also discovered in cosmic rays. And the other one is a tau, discovered in particle accelerators. And then in between them, we have the neutrinos. I won't be saying so very much about the neutrinos, but they also play a very important role in the evolution of the universe. So these are the fundamental constituents of matter. But in order to make matter, you need interactions. And here is a list of the 4 fundamental interactions. There's gravity, which of course has been a lot in the news recently with the discovery of gravitational waves. Then we have electromagnetism. So of course the 2 parts of the word electromagnetism are both Greek words. So electromagnetism was unified almost exactly 150 years ago by James Clerk Maxwell. And that force, that interaction, is carried by a particle called the photon, which we'll come back to later on. Then inside matter, we distinguish two other fundamental forces. There's the strong nuclear force that holds nuclei together, and then there's the weak nuclear force, which is responsible for forms of radioactivity. So what you see on this slide is sufficient to construct all the visible structures in the universe. Oh yes, James Clerk Maxwell was professor at King's College London. So I like to think of what you see on this slide as being in some sense the cosmic DNA that contains all the information encoded to make galaxies, stars, planets, even Donald Trump. With one exception. There's one thing missing on this slide, and that is an explanation of where the masses of the particles come from. For example, we know the electron has to have a mass, otherwise you would not have any atoms. Electrons would run away from nuclei at the speed of light. This particle here that carries the weak nuclear force, that has to have a large mass, otherwise the weak nuclear force would not be weak. Radioactivity would be very strong. We'd all glow in the dark. So we need to understand where particle masses come from, and that's the missing piece, what was the missing piece of the Standard Model until the discovery of the Higgs boson. So I talked about Gauguin's questions. Let me now translate those questions into the language of particle physics. So what are we? That becomes what is matter made of? Corollary of that, why do things weigh? What is the origin of mass? What is the origin of the matter in the universe? Where do we come from? What is the dark matter that fills the universe, without which galaxies would not be brought together? Where do we come from? Where are we going? How does the universe evolve? Why is the universe so big and old? What is the future of the universe? Where are we going? So these, I think you will agree, are very fundamental questions, Gauguin's questions, and our job as particle physicists is to ask those questions and hopefully answer at least some of them. So Peter Higgs, his boson, provides an answer to one of those questions, and it may be related to the answers to some of the others. Many of these questions are being studied in other experiments at the Large Hadron Collider, the LHC, and just now we are starting a second run of the Large Hadron Collider at higher energies, which will give us the opportunity to look to see whether there are other particles, other forces, other interactions above and beyond the Higgs boson. Okay, so let's talk a little bit more about mass. So Newton, of course, related mass to weight. Einstein said that E is equal to mc squared. Unfortunately, these two guys somehow forgot to explain where the mass comes from in the first place. And that, as I've already said, is where Peter Higgs comes in. So here on this blackboard behind him is his formula, but you probably can't read that, so I will now reveal it to you. My wife will be relieved to know I'm not going to take any more clothes off. Okay, so the top line of this equation represents the fundamental forces. The second line, if you can see it, that is how those forces act on fundamental particles. The third line is how we think the Higgs boson gives masses to the fundamental particles of matter. And the bottom line, that's how the weak interaction becomes weak. So that's the theory. And you will see that this theory involves something called phi, another Greek letter. That phi is a field, a little bit like the electromagnetic field, but different. And associated with that field, there is a particle, in the same way the photon is associated with the electromagnetic field. That particle is the Higgs boson, and between 1964 and 2012, when it was finally discovered, the Higgs boson was in some sense the particle physicists' holy grail. I perhaps should also mention that Peter Higgs was a student at King's College London. So what was the basic idea of Peter Higgs and his colleagues who also proposed this theory? So the basic idea is that all of space, even empty space, you should think of as a sort of medium, a medium through which other particles propagate or traverse. So let me compare it to a snowfield. Imagine that you're in the middle of Siberia, in the middle of winter, and there's a field of snow extending in all directions as far as the eye can see. Homogeneous, isotropic, universal. Now imagine that you are a person trying to go through this medium. So if you're lucky, you might have skis. If you have skis, you skim across the top of the snow. You don't interact deeply with that Higgs snow field. You go very fast. That's like a particle that does not interact with the Higgs field, a particle like the photon that has no mass and travels always at the speed of light. So skier, photon, speed of light. But maybe you've got snowshoes. If you've got snowshoes, then you sink into the snow, you interact with that Higgs field, you go slower than the skier, like a particle with mass that interacts with the Higgs field and always travels at less than the speed of light. And then finally, maybe you try to walk across Siberia in your boots. Well, that'll take you a long time. You're going to go very slowly, much less than the speed of light, because you're interacting very deeply with that Higgs snow field. So that's the basic idea. A universal medium, what we call a field, and your mass depends on how strongly you interact with that field. But how do you know that that field is there? How do you test this theory? Well, what is snow made of? Snow is made of snowflakes. So we think that there is a fundamental quantum, a fundamental unit, if you like, of this Higgs field, the Higgs boson, in much the same way that the photon is the fundamental particle of light. And so this is what the LHC looked for, and this is what the LHC found in 2012. Now you can carry this analogy a little bit further. So all snowflakes are different. And that's because they're made up of other little things inside. They're made up out of water molecules, which can be arranged in different ways. And right now, we're having a big argument as to whether the Higgs boson that we discovered is the only Higgs boson, or whether there are other Higgs bosons, whether there are things inside the Higgs boson. And these speculations have been encouraged by a possible discovery at the end of last year, which I will mention right at the end of my talk. So, as I mentioned, the idea was proposed by Peter Higgs back in 1964, and my own personal interest in this started in 1975, a paper that I wrote with Mary Gaillard and Dimitri Nanopoulos, where we made perhaps the first systematic study of what this Higgs boson particle might look like and how you might actually discover it. Now, at that time, these ideas of the Standard Model were regarded as quite speculative, and certainly the existence of the Higgs boson was regarded as being very speculative. So we're a bit cautious at the end of our paper. We wrote, we do not want to encourage big experimental searches for the Higgs boson. Fortunately, our experimental friends did not take our bad advice. So they thought about looking for the Higgs boson. So how do you set about finding it? Well, you need to collide particles at high energies. And this is a simulation of a collision between two protons at the LHC. their energies are converted into lots of other particles, charged particles, which you see here are these yellow lines, and neutral particles, which you see here as these blobs. Now, you don't see the Higgs boson directly because, well, first of all, it's neutral, it doesn't leave a track, and anyway, it has a very short lifetime. It decays very quickly. But what you can hope to see is what it decays into. And in this simulation, it decays into 2 energetic particles over here and 2 energetic particles over there. So what you have to do is you have to trawl through billions and billions, trillions of events, and among the hundreds of particles that are produced, look to find what this Higgs boson might have decayed into. Okay, so just a little bit about the relationship of all this research that we do to cosmology. So I just want to remind you a little bit about where we come from. So if you go back towards the Big Bang, if you go back to less than 300,000 years after the Big Bang, there were no atoms. So when the universe was less than 300,000 years old, no chemistry, no biology, only physics. If you go back when the universe was less than 3 minutes old, there were no nuclei. Before then, there were protons and neutrons and electrons running around, but no nuclear matter. If you go back when the universe was less than 1 microsecond old, there were not even any protons and neutrons. There were quarks, there were electrons, but there were no protons and neutrons. And if you go back to when the universe was a picosecond old, so a millionth of a second old, that's when we think that the Higgs idea came into play and particles acquired their masses. Before then, they would all have been massless. Somewhere around this time here, we think maybe when particles of dark matter emerged from the primordial soup, and somewhere around here also maybe the time when matter originated. But I'll come back to those issues later on. Okay, so how do we explore all these things? As I said, we need to collide particles at very high energies, and that's where the Large Hadron Collider comes in. So here we are in its tunnel, 27 kilometers underground. You can see the slight curvature here of this line of magnets. So when the thing is operating, there are thousands of billions of protons circulating in both directions through those magnets. Each of them has approximately the energy of a fly, and when the thing is operating, they make billions of collisions per second. And in those collisions, we hope to find the origin of mass, maybe discover dark matter, maybe understand the small difference that exists between matter and antimatter. So as I already mentioned, we've just started a new round of experiments with the LHC at higher energies than was possible previously. And if you translate that into cosmology, it means that we're now exploring the laws of physics sometimes something like 3 times earlier in the history of the universe. Now, in order to do this, we require our engineer friends to give us a lot of help. So one thing that they have to do is to provide us with the emptiest space in the solar system. So here we've got the magnets, here we've got tubes, the particles go through those tubes. We want those particles to collide. We don't want them to hit molecules of gas. And so we have to remove the gas as much as we can from those tubes and create a vacuum which is similar to interplanetary space. The pressure in the beam pipes is lower than on the surface of the moon. Now, in order to keep the particles going around at very high energies, we need very powerful magnets. Those we can make by going down to very low temperatures. This is part of the refrigerating system of the LHC. And those magnets are cooled down to a temperature 1.9 degrees above absolute zero. So if you compare that with the temperature of interplanetary space, that is filled with radiation with a temperature 2.7 degrees above absolute zero. So I like to tease my cosmological friends by saying that particle physics is 0.8 degrees cooler than cosmology. Okay, so we've got the protons going around, we've got them colliding, and so then we want to look at what happens when those particles collide. To do that, we have large detectors. So there's ATLAS and CMS that discovered the Higgs boson are now looking for particles of dark matter. And then there are two other more specialized experiments, Ellis, which is trying to understand the primordial cosmic plasma, and this one which is looking at the small differences between matter and antimatter. And I mentioned previously that they're Greek physicists working at CERN. They participate in ATLAS, CMS, and the Ellis experiment. So this is a sort of time-lapse series of photos showing the assembly of the ATLAS detector some years ago. And this is a final view before the inner part of the detector was placed in it. And here you see a person. This is a full-size person. This is not a Lego person. That's a real person. It's something like 25 meters in diameter and almost 50 meters long. And to put that together required an enormous international team of some 3,000 scientists and engineers. There was 1,000 PhD students working on this detector. They're the people who do the real work nowadays. And they come from 38 countries, including, for example, Greece. And that device has more components than the rockets that took people to the moon. So, what did they do? What did those graduate students discover? Well, in 2012, they discovered the Higgs boson, and that generated a sociological phenomenon that I call mass Higgsteria. So what was that based on? So I mentioned earlier the sorts of events that the experiments would look for. And here's one example of an event seen by the ATLAS people that looks just like what one would expect a Higgs boson to look. So this is a computer reconstruction of the detector. You can see the charged particles coming out. You can see the blobs of neutral energy. And you can see 1, 2, 3, 4 very straight red lines. Those represent 4 energetic charged particles that might have been produced by the decay of a Higgs boson, just like on that simulation I showed you a few minutes ago. This is an event which was observed by CMS. So here you see, again, the charged particles, you see the blobs of neutral energy, and here in red you see 2 very large blobs of energy. And those, we think, are 2 energetic photons that might have come from the decay of a Higgs boson. That's a decay of the Higgs boson that, with my colleagues Mary Gaillard and Dimitri Nanopoulos, we calculated back in 1975. Now, if you see just one event of that type, you can't be sure of what it was. But if you see enough of them, then you convince yourself that you're seeing something real, and that's what happened on July the 4th, 2012. So here are some newspaper headlines. Here is a picture in the main auditorium of CERN on that day. You see lots of happy physicists. You see this guy with his back to us, that's Lynn Evans, the guy who built the LHC accelerator. And this guy over here, this is Chris Llewellyn-Smith, the Director General, who persuaded European countries to build the LHC. This is a picture that I like for 2 reasons. One reason is here you can see Peter Higgs, and this is François Englert, a colleague who independently proposed this idea of this universal medium responsible for particle masses. And although they proposed the idea back in 1964, they had never met until this day 48 years later in the main auditorium. So that's one reason why I like the picture. And the other reason is that here you see Fabiola Gianotti, who was leading the ATLAS experiment at the time. So she was one of the people who announced the discovery of the Higgs boson, and now she is our boss. She is the Director General of CERN. So what did these experiments see? Well, here I show, as a function of the possible mass of the Higgs boson, the data with the background from other types of events subtracted. So if you see anything which is non-zero, that would possibly be a Higgs boson. But you see here the data are sort of fluctuating around. There's nothing very much going on. No Higgs boson on the left, no Higgs boson on the right. But if I remove the white rectangle, then you see a very significant peak, an excess of events, certainly a new particle. And the question was, is this the Higgs boson finally emerging from the background? So for 2 or 3 years after the discovery of this new particle, theorists and experimentalists were working very hard to try to understand whether this really was the final missing piece of the particle Higgs-Thor puzzle, or whether it was possibly some sort of imposter that looked like a Higgs boson but actually wasn't. So this is something that I personally have been working on with my former PhD student, Tivong Yu. And well, one of the things that we asked ourselves was, the Higgs boson gives masses to other particles. That means that its couplings, its connections with other particles, should be proportional to their masses. What do the data say? So the data give you these little black lines here. The theory of the standard model gives you this red line here, and you can see that the data are completely consistent with the theory. Peter Higgs can smile, and we wrote in our paper that this particle walks and quacks like a Higgs boson. Now, more recently, this type of analysis has been done much more precisely by the ATLAS and CMS collaborations, and this is the latest data. And so here you see how the Higgs boson connects to many different other types of particle as a function of their mass. Everything is in perfect agreement with the standard model. So, 48 years after the Higgs boson was proposed, it was finally discovered. That 48 years gave Peter Higgs time to evolve from this picture to this picture. Now, the Higgs boson is certainly very important. Without it, there'd be no atoms. As I mentioned, electrons would run away from nuclei at the speed of light. There actually wouldn't be any heavy nuclei. The weak interactions responsible for radioactivity would not be weak. Life would be impossible. Everything would be radioactive. So the discovery of this particle was indeed a very big deal. And that's, of course, why the Swedish Academy in 2013 gave the Nobel Prize to Peter Higgs and to François Englert. And in their citation, they said, "Today we believe that beyond any reasonable doubt, it is a Higgs boson," the particle that was discovered in 2012. And my student and I were very proud because that quotation was taken from one of our papers. But what they didn't know was that it's not in the published version of the paper. Because when we sent our paper to the journal, the expert who reviewed the paper said, no, beyond any reasonable doubt is not a scientific judgment. So the unpublished version has that phrase in, and it's good enough for the Nobel Prize Committee, but not good enough for the journal. Okay, so the discovery of the Higgs boson, in some sense, marked the completion of the Standard Model. So you might be asking whether there is anything beyond the Standard Model. And my answer to this is based on that well-known scientific expert, James Bond, who told us that, I paraphrase, the Standard Model is not enough. So why do I say that? Well, as I'll mention in a moment, in the Standard Model, if you calculate the properties of empty space, you discover that it's unstable. The Standard Model does not explain the origin of dark matter. In fact, it doesn't explain the origin of matter itself. Other puzzles, neutrinos, why do they have masses? What explains the hierarchy of different mass scales in physics? Cosmological inflation is our theory of why the universe is so big and old, but we don't have a model for that within the Standard Model. We want to make a quantum theory of gravity. I could go on, but here I just restrict myself to listing 007 reasons for thinking there must be physics beyond the Standard Model. Now, there's a theory which I like, some of my colleagues also like, called supersymmetry or SUSY, that I think helps provide answers to at least some of these problems. I'll mention that briefly in a moment. The good news from the experimental point of view is that the second run of the LHC, which is proceeding at the moment, will address several of these fundamental problems and maybe will provide some answers to some more of Gauguin's questions. So let me talk a little bit about empty space. So in the Standard Model, you can try to figure out what is the destiny of empty space. What's going to happen to empty space in the future? And this depends on the properties of the Higgs boson and of the property in particular of the top quark, the heaviest quark. And for certain values of their properties, empty space is stable, the universe can continue forever, but for other ranges of their properties, the universe is unstable and our vacuum will eventually decay. Not soon, not next week. Donald Trump will destroy us quicker. But eventually, according to the Standard Model, the universe might be unstable. And the measurements of these particle properties indicate that, at least within the Standard Model, we're in this unstable regime. Now, of course, I don't believe that the universe is going to collapse. I think there must be new physics to stop it from collapsing, and my favorite, supersymmetry, is one of the theories that would indeed prevent that collapse. Supersymmetry could also provide the dark matter that I mentioned on a couple of occasions. So here's a typical galaxy. The stars are going around and around. They're held together by gravity. But whose gravity? Because the gravity that's generated by the visible matter, the stars, is not sufficient to hold that galaxy together. If that was the only gravitational force, the stars should fly apart. In fact, there must be additional matter that generates additional gravitational attraction to hold those galaxies together. And that could be supersymmetric particles. So according to supersymmetry, all the known particles have partners which have the same, for example, electric charge, but have in general much larger masses. And even the lightest of those would be so much heavier than ordinary matter that if it's present in the universe today, it could provide the dark matter and explain the existence of galaxies. So how do you look for this dark matter? So dark matter doesn't shine. It doesn't send us photons that we can see. So how do you see it in your detector? The answer is, of course, that you don't see it. But that dark matter carries energy and momentum. So what you do is you look for events where the energy and momentum are unbalanced. For example, here in this computer simulation, I've got a whole bunch of regular particles coming out here, carrying energy and momentum, but nothing very much going out on the other side. Now, of course, momentum must be balanced. If you bang two billiard balls together, then they will bounce back in opposite directions. So the interpretation of events like this, if you saw one, would be that there have to be particles coming out which you cannot see, potentially particles of dark matter. So the experiments Atlas and CMS who've already been looking for such events, they haven't seen any interesting ones, and that's one of the searches that's going to be continuing now with the ongoing run of the LHC. There's a lot of interest in antimatter. In fact, the CERN press office tells me that they get more media inquiries about antimatter than possibly anything else. Whether that's because of Star Trek or because of Tom Hanks, I don't know. So why do we study antimatter? Well, we can't make enough antimatter to power up the Starship Enterprise or even to destroy the Vatican. What we're interested in is the microscopic difference that apparently exists between the properties of matter and antimatter. So antimatter was postulated back in the 1920s by Paul Dirac, putting together relativity and quantum mechanics. He realized that every particle had to be accompanied by some particle with opposite internal properties, opposite electric charge, but identical mass. And antimatter was discovered in the cosmic rays a few years later, and it's actually used nowadays routinely in medical diagnosis. It came as a big surprise when people discovered that matter and antimatter are actually not quite equal and opposite as Dirac and others had thought. And it may be that this very small difference between matter and antimatter explains why it is that in the universe today there's matter in galaxies, but there's no visible amounts of antimatter. And that's one of the things that we're exploring with the LHC, and there's a dedicated experiment trying to understand this matter-antimatter difference and the possible connection with the origin of the matter in the universe. Of course, we physicists also dream of eventually making a unified theory of all the fundamental interactions. This was certainly the dream of Einstein, but he never succeeded. That's maybe why in this picture he looks a little bit sad. But we're continuing with many of his ideas. In particular, he worked on the idea that there might be, in addition to the three dimensions of space that we know about, additional hidden, invisible extra dimensions. Now, in some of those theories with extra dimensions, gravity could possibly become a strong force already at the energies of the LHC, and in that case, conceivably, at the LHC in collisions, you might be able to make microscopic black holes. Now, this got a few people worried that maybe these black holes would eat up the entire Earth. But don't worry, these are very, very small black holes that disappear instantly. This is a simulation of what one of these black holes might look like. And just to reassure you that you shouldn't worry about them, remember that the Earth has been bombarded by cosmic rays for billions of years, and we're still here. Unfortunately, we haven't yet seen any microscopic black holes at the LHC, but we're still hoping. So as I've mentioned, experiments at the LHC have restarted at higher energies. So last year already we started making collisions at what we call 13 TeV. That's about 13,000 times the rest mass energy of the proton. And something very unexpected showed up. So imagine that you're in Plaka with a group of your friends, and you've ordered a whole bunch of mezes, and they arrive on the table, and you cannot remember who ordered that one. So the physicist Rabi, when the muon was discovered in cosmic rays, asked exactly that question. Who ordered that strange particle? Actually, we still don't know. Something very similar happened at the end of last year when Atlas and CMS reported observation of some sort of statistical effect which might conceivably, perhaps, possibly, maybe, potentially be another new particle. So it would decay into 2 photons, much like the Higgs boson decays into 2 photons. Now, you may have heard the Higgs boson described as the God particle. We physicists don't like that name. But if the Higgs boson is the God particle, I'd like to know what this is. Anyway, we don't yet know whether this particle is real, but if it is real, then I think it would be the tip of a new iceberg of new physics beyond the standard model. And so we're all waiting with great interest to see whether this particle is confirmed with the data that the LHC is taking this year. So that brings me to the end of what I wanted to share with you. I hope I've convinced you that the LHC is the world's most powerful microscope, looking deep inside what we are made of. But in some sense, it's also one of the world's most powerful telescopes, able to look back to the beginning of the universe, where do we come from, and perhaps also telling us something about where we're going, what is perhaps the future of the universe. Ευχαριστώ.